We don't need to record it. Okay, without further ado, Mike's going to continue on Fracton.
Okay, thanks, Leo, and thanks to all of you. So I just want to get right into it. So there was more that I wanted to say about the U1 spin liquid example from the end of last lecture, but I think in the interest of actually getting to fractons like soon, I want to just move on. And so I'm going to give you another example in just a minute, but first I want to just note some property that both the examples from yesterday satisfy, which is going to be sort of the key difference with fracton states. Okay, so in both examples, the excitations are mobile, are gapped quasi-particle excitations above the ground state are mobile. So here, excitations, I'm thinking about E, M, and F in the Z2 spin liquid, or the electric and magnetic charges in the U1 spin liquid. So what is this? So this almost, like normally, this almost doesn't warrant any sort of comment. Like we have quasi-particles. Of course, they're mobile. That's just what quasi-particles do. But that's exactly what's not going to be true in fracton states. So we actually have to think about what we mean by mobility. Okay, so what does it mean? Well, let's suppose we have an excitation here. I'm going to call it E because it could be E in the Z2 spin liquid. It could be something else. And let's imagine that we have some translation. So I'll call the translation group T. And let's pick some particular element of it. So this will be a translation by some lattice vector. Okay, and we have an excitation E that's sitting somewhere in some state. We can imagine making a new state where we move it by our translation. Okay, and this is not mobility. You can always do this. Okay, the key question to ask is, does there exist a local operator, meaning it's supported in this region, containing both this excitation and this excitation? Let's call it U because often it's unitary, that destroys E and also at the same time creates TE. So that's what it means for this excitation E to be mobile. Okay, and if you think about it, why is this a reasonable definition? Well, another way that you could think about mobility is just that you say, imagine this excitation E is not an eigenstate of our Hamiltonian. So we start with a system where E is here, and then we run some dynamics. It doesn't actually have to be Hamiltonian dynamics. It could be any sort of local quantum dynamics. And then we wait for a while, and then we can just ask, like, well, did it move over here under this dynamics? So if this is true, it's possible for E to move over here. There will be some amplitude for that to happen, basically under any reasonable dynamics. Okay, well, maybe not always. Like sometimes this could depend on issues of energy conservation and so on, right? This excitation and this excitation might cost very different energies. Okay, this won't necessarily happen, say, under energy conserving dynamics, that you have an amplitude to go from here to here, but there will be some dynamics under which it will happen if there exists some local operator that moves E to TE. Okay, so so it's important to sort of contrast this with, let's say, localization in Anderson insulators, where there are excitations that are stuck, but the reason that they're stuck has a lot to do with energy conservation, right? If you don't have energy conservation, then there's no immobility in Anderson insulators. Excitations can move around just fine from one localized state to another. This property is still true in any, right? There always exists a local operator move excitations around in a localized insulator. This is something different. It's a different kind of statement. Yeah.
Say that the excitation excitation are created with string operators?
So, yes, this is always true for excitations that are created with string operators. Well, actually, no, not completely, not completely. So I'll talk about subtlety in the Z2 spin liquid, which is important to understand actually in just a second. Okay, but so this is, so, if U exists, E, we can say E is mobile along the translation T or in the T direction or whatever you want to say. Okay, so yeah, that's the board I want. Okay, so right, so here's the example that I wanted to talk about. So here's a subtlety. So let's think about the Z2 quantum spin liquid. Suppose we have translation symmetry. So I'll say this is Tx, Ty, so we're in a 2D square lattice or something. And let's suppose that Tx acting on E is actually an M excitation, okay? And Tx acting on M is actually an E excitation, not at the same lattice point. That's why I wrote this symbol. And the same thing could be true for Ty. It doesn't really matter. Let's assume it's also true for Ty. So both Tx and Ty, they permute E into M and M into E. Okay. So in this case, there's no local operator that transforms E into Txe, which is M, because that's actually what it means for E and M to be excitations of different types. It's exactly the statement that there's no local operator that will transform an E into. Okay, so in this case, E is not mobile along T. Okay, however, right, so this is a phenomenon that occurs, but it's still true. You can ask, well, what if you translate twice in the x direction? Then clearly you come back to an E. So Tx squared acting on E is still an E-type excitation. So now E is mobile along a double translation, Tx squared. So if you translate far enough, E is still mobile, but it's not mobile under the very shortest distance translation. So this is something that can happen. You can actually realize this in the toric code. I explained this as part of an answer to a different question after yesterday's lecture. I explained how you can do it. I don't want to explain it now, but if you didn't hear that and you want to know how you can realize this in the toric code, I'll explain it after the lecture. Okay, what this sort of subtlety points out is that what we mean by, when we say an excitation, if we say an excitation is mobile or fully mobile, sometimes people say, what we really mean, we mean it's mobile over sufficiently long distance. Okay. And it's actually true that can we turn on the light in this middle section? So in topological spin liquids like the Z2 spin liquid, there are always a finite number of excitation types, and that actually implies that any excitation is always mobile over sufficiently long distances. Okay.
In this case, you would say it is mobile because
yeah,
you don't care that it's
I would still say, yeah,
too out of sight.
I would still say that the E excitations are mobile here, but if you ask about very specific translations, you can get more subtle results, right? But, and this is sort of, it fits with our intuition because sort of what we'd like to know is like, if we make an E wave packet somewhere in space and then we evolve with some dynamics, energy conserving or not, and we wait a while, we'd like to know, does that wave packet spread out in all directions in space? And the answer is that it will, okay? Unless you pick your, you really fine tune your dynamics, right? But imagine you don't do that. Okay, so, all right. So that's kind of a preamble to talk about two examples of models that have fractons. So the first one is often called in the fracton business, the scalar charge theory. And so there's some prehistory, but the key work was done by Michael Pretko in 2016 as part of his PhD thesis. Okay, kind of an amazing single author paper when he was a graduate student. So we're going to be in 3 dimensions. And this is kind of similar to our U1 spin liquid example. That's why I mentioned that example. Okay. And so it's also a kind of U1 gauge theory, but the difference is that instead of the electric field being a vector, which is what we're used to, the electric field is a tensor. So there's a tensor electric field. I'm gonna, I'm sort of writing this down, you can imagine, in the continuum, but well, I'll make some comments on that. I'm not really thinking about a continuum theory. I'm just being sort of schematic, because to write it down in detail on the lattice, which is what you really should do, will take too long. And there's a lot of other things I want to explain to you. But there's a tensor E field, which is a rank 2 tensor, and we'll assume that it's symmetric. And mu and nu are spatial indices, so they can be x, y, or z. Okay, and there's a Gauss's law. So this electric field satisfies a Gauss's law with 2 derivatives. We could also write them as lattice derivatives, like finite differences. But the point is that this double divergence of E mu nu is a scalar rho, and that's the charge. So that's the form of the Gauss's law. The charge is a scalar. That's why it's called the scalar charge theory. Once you start thinking about electric fields that are tensors of various kinds, there are many, many games that you can play. You could imagine that the charge doesn't have to be a scalar, for example. And there's a whole zoo of these theories, which is very interesting, but I'm just going to talk about this one. Okay, and what I'm going to write down schematically is that, so we can write down, so we can construct, if we start with this idea, we can construct a Hilbert space with these electric field degrees of freedom, and we can write down an effective Hamiltonian for a deconfined phase. This theory does have a deconfined phase in 3 spatial dimensions. I mean, that's a non-trivial statement. There are things that have to be checked. But our Hamiltonian looks schematically like E squared plus B squared. So what's B squared? Well, I'm not going to tell you in detail, but if you do ordinary gauge theory in the Hamiltonian, the objects that you work with are the electric field and the vector potential, A mu, and they're canonically conjugate to each other in the Hamiltonian. But the vector potential is not gauge invariant, so it can't appear in the Hamiltonian. But so you can construct the gauge invariant magnetic field out of the vector potential, and then that can go into the Hamiltonian in a B squared term. So very similarly here, there's a tensor potential, A mu nu, which is not gauge invariant. Gauss's law tells you how it transforms under a gauge transformation. From it, you can construct the magnetic field, which in this case is also just a single derivative of the tensor potential, and you can construct something like B squared. Okay, and there are also some dynamics. There's dynamics for gapped electric and magnetic charges. I won't talk about the magnetic charges at all, actually, but they exist and they're gapped. Okay. There is also, like in the U1 spin liquid example, there's a gapless photon. It's different from ordinary photons. One thing that's different, you can do some simple counting. And I'll leave this as an exercise. It's a very simple exercise to do this counting. You can figure it out with what I told you. There are 5 polarizations of this photon, okay, instead of 2 for the photon that we're used to in ordinary E and M. Okay. All right. So it's important that this can be realized on the lattice in a spin model without any special symmetries. And I had actually wanted to tell you something about how that works for the U1 spin liquid. That's what I skipped. But I think that's okay. The way that, like very roughly, the way that it works here is that you can do this on a cubic lattice, and the diagonal components of the electric field tensor kind of naturally live on lattice sites. So you need 3 diagonal components on sites, EXX, EYY, EZZ. And then the off-diagonal components naturally live on faces of the cubic lattice. And with that sort of geometrical idea in mind, you can build everything up from there. Okay. And it's also true that you can write down a spin model, really a spin model, like something that's not obviously a gauge theory when you write it down. It doesn't have any special symmetries or special structure. It's quite generic. For which the low energy effective Hamiltonian is of this kind. So this is definitely a phase of a spin model that exists. It's not a realistic spin model at all. The main thing that's not realistic about it is you need sort of a weird pattern of spins in space and sort of a weird geometry of interactions between them. But the interactions that you need are still local. Okay, the kind of difference from the U1 spin liquid example is that there's sort of a miracle that happens that there actually are ways to realize that example on a lattice which actually occur in real materials. Whether or not that phase occurs in real materials is still an ongoing story, but that effective description definitely is relevant for a large class of real materials on the pyrochlore lattice. And that is kind of a long and ongoing story that goes under the heading of quantum spin ice. Okay, we don't get so lucky for this example, but maybe there are other examples of this sort of general type for which we do get lucky, but we don't know yet. Okay, anyway, I think I saw a question back there. No question. Okay, so okay, so now remember in the U1 spin liquid, I made this argument, which I said is what it means for the electric charge to be conserved. Okay, so let's consider the same sort of thing here. Okay, so and here something interesting is going to happen. Okay, so suppose again we have some volume V, and we ask about the charge inside. So the charge inside of volume V is just an integral of the charge density, and we can put in, we can re-express this in terms of Gauss's law. Okay, and this is a total derivative. So this is clearly a surface integral. This is a unit normal, something like that. So because this is an integral on the surface, just like before, the charge is conserved by the same argument. So there's no local process here that can change the electric charge. Okay. So Q is conserved. Okay, that's the same. But we can do more actually because there are 2 derivatives here, right? So really, mathematically what you do to get from here to here is you integrate by parts, and this is just the boundary term. okay? But we could have integrated by parts again if we wanted to, right? We still have a derivative here. And so what this suggests that we should do is to consider the dipole moment. Okay, so the dipole moment in this volume, it's a vector, and it has the following expression. Right, it's just a moment of the charge density. So we just put x mu, multiply it by rho, and we integrate. That's the dipole moment. We can plug in Gauss's law. Not mess up my indices. Okay, now we can integrate by parts twice. I won't write down the expression, right? But the point is when you integrate by parts the first time, what you get, well, you'll get some boundary term, but then you also get a term where this del nu hits x mu, and it just gives you a constant. And then you can, and that still gives you something non-trivial in the bulk, but then you can integrate by parts again. And then you can get something that only lives on the surface. And so the point is that you get some function of the general form of what you can get is some function f mu nu of the electric field tensor dotted into the unit normal and nu integrated over the area. So again, it's a surface integral, right? Only of the electric field. And so by the same argument from yesterday, this actually tells us that there's no local process that can change the dipole moment, okay? That's very different. In ordinary U1 gauge theory, there definitely are local processes that can change the dipole moment, right? You can create a particle-hole pair close together in space. There's no problem with that. But here, that's different. So we say that the dipole moment is conserved. All right. And so now what we want to do is we can ask about the consequences of this for the mobility of a single electric charge. And let's now do this on the lattice. Let's imagine that we're on the cubic lattice, which is where it's easiest to define this theory. So we put a charge here, Q equals +1, okay? And microphone issue there. Okay, so what we want to ask about is like, you know, can we move this charge over 1 unit to the right, for example? I mean, we could ask this for any position, right? So let's draw the same piece of the lattice. Now the charge is not here anymore, it's over here. Okay, but this process, I don't mean equals, I mean an arrow. This process changes the dipole moment by the lattice constant times x hat, if this is the x direction. Okay, so this is not, it's not allowed. There's no local process that can do this. So no local operator can realize this process. And actually, that's not true just for this translation by 1 unit to the right, but it's true for any translation of our charge to any lattice site, right? Because, right, you'll always be changing the dipole moment by some amount if you want to take this charge and move it somewhere else. Another way to think about it is like, what charge configuration do you have to add to this picture to get to this picture on the right? Well, the charge configuration that you have to add is minus here and plus there, which is exactly an electric dipole, right? So that's what your process will have to do. You have to add a dipole to the system, but that dipole is conserved. You can't add it locally. And if you want to move this charge anywhere, you have to add some dipole, just a different dipole. So no local operator can realize this process for any translation. And so the consequence is that these charges, a single isolated charge, the charges are immobile. by our definition. And this is what it means for an excitation to be a fracton. So a fracton is a kind of excitation which is immobile in this sense. Okay. Okay, so this is something different. So this sort of funny tensor gauge theory, it has charge excitations that have some kind of restricted mobility, right? And I mean, the mobility is very restricted. If you have a single one of these excitations in isolation, it just doesn't move under any dynamics. Yeah. Well, I mean, okay, so I'll give you an example where this phenomenon does not arise from a conserved dipole moment. You know, in some sense, charge is just a label here, right? So it's important to emphasize that this theory has it doesn't require any global symmetry except translation. You need some level of translation symmetry to talk about this phenomenon in a precise way. But there are certainly no internal symmetries. There's no globally conserved charge here. In the deconfined phase of a gauge theory kind of behaves like there are conserved charges. But that's something like that is kind of true in any state where you have fractional excitations. So that's just kind of a point that I want to emphasize. It's also true that this immobility phenomenon, it does not always come from conserved dipole moment. Although it doesn't always come from conserved dipole moment. There are many other ways that we know to realize similar phenomena. Yeah, there was another question. So if I remember correctly, I didn't have a chance to remind myself of this before. If I remember correctly, the magnetic charges they're not fully mobile. They have some restricted mobility, but they're not fractons. So I think they can move. If I remember right, I think they can, they have a vector character and maybe they can move, depending on their vector, they can maybe move in the plane perpendicular to that vector or something like that. It's something roughly like that. Yeah. So and we'll talk about another example where we'll see other kinds of restricted mobility, which are not just this kind of very extreme case of fractons. So there are lots of different kinds of restricted mobility excitations. Yeah. Question. Well, there are no in this theory, there are no quasi-particles that carry fractional charge. You could have a phase transition into some other phase where there are fractionally, quasi-particles that carry fractional charge under this tensor gauge field, but I'm not talking about that state. Well, I mean, so if you realize it's just the unit of charge, basically. Whatever the smallest charge you can make is, you call that 1. There's nothing magical about it. So to really answer your question, I have to write this theory down on the lattice, but I'm not going to do that because it takes too long. Yeah, but right. But the way to realize this theory quantum mechanically, so this electric field should be it should be something like the z component of a spin operator, or it should be a quantum rotor variable. It should be something discrete. So there's already some quantization built in. You could imagine trying to make a theory like this where the electric field actually has real eigenvalues. But I think, first of all, that's not going to happen so that will not be an effective theory for a quantum spin model with a finite dimensional on-site Hilbert space. That's the simplest answer. So you can definitely write down quantum theories like that, where the charge is a real number, just like you can imagine writing down QED, where real number, like arbitrary real charges are allowed. But I think the simplest answer is you can make good arguments that theories like that cannot occur as low energy effective theories of a quantum spin system. Yeah.
You need to really have Quantization, you need compactness of the gauge.
Yeah, I phrase it in terms of discreteness of the electric field, but that's kind of the same thing as compactness and the
that's,
magnetic
You know,
variables.
that's already implied by the fact that you say you have monopole.
Yeah, that's true. Yeah. Other questions? Yeah.
Yesterday, you talked about having a boundary condition in the toric code or where it changed E to M, moved the particle around.
Right.
And so that's not something I'm a little bit confused about that. And also like this statement over here that you have a situation where TXE is like M.
Well, those two things are closely related. I don't know if I want to go all the way back there now.
I guess even this,
but,
yeah, you know, more
like, so the fact that you can have the easiest way to construct a system with that boundary condition where E turns to M is to start with a version of the toric code where translations do this. And then you would pick an odd by even torus, and then you have a boundary condition that does that.
yeah, okay. But this doesn't happen in like the ordinary toric code model.
Actually, it does.
It does?
Yeah, it does, but not for, but it's for what you, it's a translation, kind of a smaller translation that exchanges vertices and plaquettes.
Okay.
And you have to do an internal rotation in the spin space along with it. It's only a symmetry when the coefficient of the AV and BP terms are equal. But there is an extra translation symmetry in that case. You know, because it takes vertices to plaquettes, it really has to take E to M. But it is just for the ordinary toric code. Yeah.
It's like a hidden translation that you don't see that's
Yeah,
followed by this.
that's right. Yeah.
translation.
Yeah, it's like translation plus electric magnetic duality, kind of. Yeah, or I mean, it is kind of an electric magnetic duality operation. Yeah. So the photons here are completely mobile. In tensor gauge theories, the photon-like excitations are always mobile. I don't think there's a way to make them immobile that we know of. There are. Well, yeah. So I think you could ask, like, can you have you know, to what extent can you have gapless restricted mobility excitations? That's a more general question, not just photons. So that is a bit more, it's a bit more subtle. Yeah, I don't know. I mean, I think the answer is yes, but you know, you have to be very careful about things like fine tuning. It's very subtle. It's not something that we don't understand that nearly as well. I think it's been a little while. There are some relevant examples that I've thought about. It's just been too long for me to like give a quick answer. But you know, there's much less understanding in that direction than for gap excitations. Yeah, because you really have to worry about stability or lack thereof, and it becomes pretty tricky. I guess another point is that, oh, I can comment on that after I say the next thing I want to say, and comment on why it's a hard question. Yeah. Well, okay, this is a gapless state, so you wouldn't really expect that. But so I mean, the short answer is just no. But you know, it's a very subtle question. I wanted to not talk about, I had written some remarks down on this, but I don't want to say too much about it. But okay, let me make some comments, but not write this on the board because this is an interesting issue that I wanted to talk about. So you can, if you go read the early fracton literature, meaning shortly after Pretko's paper, you'll find statements like tensor gauge theories are great because they gave us a continuum effective field theory realization of fractons. That's total nonsense, actually. But a bunch of people who should have known better said that. Okay, you know, I mean, it was very new, so, you know, and I maybe even said it, I don't remember. So, you know, All should be forgiven, but it's nonsense. And what is true is that you can take a theory like this and you can write down its naive continuum limit. Okay, and if you do that for the U1 spin liquid example, then the continuum limit of U1 lattice gauge theory is an effective field theory for the U1 spin liquid. No big surprise. That's sort of how it usually works. So it's very tempting to think that the same thing should be true here. So there has been a lot of very nice work starting maybe 3 years after Pretko or so of people very carefully studying basically continuum limits of theories like this and a huge class of other related theories. And those theories are pretty weird. They have a lot of strange properties. I don't really want to talk about them. There's a whole series of nice works on these theories. But one thing which is really not well understood is whether those theories can be thought of as effective theories from this lattice theory that you started with. And if so, how do you think about that? Because there are certain comparisons that you can make which should hold for the way we usually think about effective field theory, which don't hold here. And the simplest one, I'll tell you the simplest one, which sort of shows that this is a confusing issue, is you can just ask how many different distinct particle types are there of gapped excitations, meaning point-like excitations that you can't transform into one another with local operators. So in this lattice theory, there's a countable infinity of those. You can have a charge, you can put it anywhere. You can also have charge 2, charge 3, charge -7. So that gives you a countable infinity. If you take the continuum limit, you get an uncountable infinity. But this kind of property, number of types of particles, or in more field theory language, would be something like number of super selection sectors, or you could also phrase it as number of different types of defects. Normally, we would say that should be the same in an effective field theory in the original system it's describing, but it's not the same here. And so that's weird. And we don't actually understand how to make that connection. So that's not something you'll find in the literature because I don't think anyone understands it. It's very confusing. I think it's very likely that there is a way to think about the naive continuum limit, some kind of effective field theory. It would be sort of weird if there's no way to do that. But exactly how and whether it's useful, that's not so clear. Yeah. Okay. Okay.
That's can we get some Winton effect kind of things going on with that?
I don't know. I think people thought about things like that, but he's wondering about things like E dot B type terms. Yeah, I think people did consider this. I don't remember off the top of my head, but I believe that there was some work in this direction. I don't know what the outcome
We had
was.
terms like this coming out,
Mhm.
utilizing lattices. If you
Right.
look at super solids, so then there's an E dot B.
Okay, yeah,
It's not the same E, there's another E, so then it's
right,
and another B, so then it's little b dot big E.
yeah. Good, okay. Were there other questions at this point? Okay, so, all right, so now what I want to say is that, so first I told you that these fracton excitations, charge excitations of the scalar charge theory, are immobile, but that's a little bit too quick to say that. I mean, it's true that they're immobile in the sense that I define, but they do have some kind of mobility, which is best thought of as a kind of cooperative mobility. And the way that we can, charge and dipole moment are conserved, but quadrupole moment is not conserved. So there are local processes on the lattice where you can do something like put in charges in this kind of arrangement or and these are the two sort of elementary processes from which you can build up other things, or you can put in charges in an arrangement like this. Both of these carry no net charge, no net dipole moment. They do carry quadrupole moment, but that's fine. So there are local terms that you can write down. They'll involve some kind of minimal coupling between matter fields and the tensor potential on the lattice. And you can write these terms down. They're perfectly gauge invariant. Okay, and so these terms do give some kind of dynamics for these fracton excitations. Okay, and what can you do if you start with a single fracton? What kind of states can it transform into? Imagine you have some dynamics where you just start acting with processes like this. What can happen? Well, the sort of thing that can happen is you start with a single charge here. And I'll think about the process on the left. So I can act with that over and over again. And I can get, let me draw a big rectangle. It doesn't have to be a square. It's close to a square. But you can have a process where you destroy this excitation and you create three charges on the other corners of this rectangle. And the operator that you need to do that is some kind of a membrane operator. It lives on the rectangle. So there's some kind of a membrane operator that will do this, sort of analogous to the string operators that we talked about before. But the weird thing about this membrane operator is that it creates and destroys excitations at its corners. It doesn't actually do anything along its edges. Okay, so this is a kind of dynamics that you can have. So one thing that's clear is that, like, if you have a translation invariant system and you have energy conserving dynamics, this process is not going to happen. Maybe it'll happen virtually, but it's not really going to happen because the state on the right will cost significantly more energy than the state on the left. These excitations are gapped, right? So this is a lower energy state than this, and so you won't get to this state. Now, if you don't insist on conserving energy, this sort of thing can definitely happen. But it's a very different, more complicated kind of mobility that requires, a lot more non-locality than just hopping of charges. Yeah. Oh, did I mess up the signs? I think I did actually. Yeah, you're right. Thanks. Yeah, thank you. Right. So this is sort of an important point, right? Like when we say that, fracton, it's not maybe 100% right to say that fractons are immobile, but they have this more complicated kind of cooperative mobility. Right? That's sort of the bottom line. Yeah.
But if I had fractons, like I could you can hop around the outside of this and give them something. Multiple.
Right. So, and that's the other, right. So you can take this further. I just gave you the simplest example, but once you have collections of more fractons, then these processes allow them to, do a lot of other kinds of motions. And of course, it's true that if you have a dipole, so if you have a plus and a minus charge, then that is a mobile particle. Nothing prevents you from moving a dipole because the kind of multipole that you need to insert to move a dipole around is a quadrupole, and that's not conserved. So dipoles here are fully mobile. Yeah. Right, and that's another sort of common feature in a lot of fracton systems, that there's some interesting structure of different types of excitations. There are some excitations that are less mobile, others that you can often make from the less mobile excitations as composites, which are more mobile. And so that is a theme that repeats itself over and over again. And it'll repeat itself in the next example that I want to introduce now. Let me see if there's any other question first before I do that. Okay, so now I want to talk about a second example, which is more like the Z2 spin liquid. And here I will actually write down a lattice model, which is very much like the Z2 toric code. So this is called the X cube model. And it was introduced by Vijay, Ha, and Fu in 2016. So in the same year as Pretko's paper, same year on the archive at least. Okay, and you know, mentioning these two examples, well, these two examples both have a lot of pedagogical value. They also have, there's some historical value because it was really these two examples being introduced that led a lot of people to start thinking about fractons over the next few years, because both of these examples were simpler than other examples that preceded them that I'm not telling you about. So again, we're in 3 dimensions. And what I will do is write down a commuting Pauli Hamiltonian. And this will be on the simple cubic lattice. With qubits on edges. Now that also would be true for these statements also would also be true for the 3D toric code, but this is different from the 3D toric code. Okay. Some other commuting Pauli Hamiltonian that you can write down. So I'll write down the Hamiltonian and then I'll draw a picture of the 2 kinds of terms that appear. So the Hamiltonian is a sum of 2 kinds of terms. So let me explain that. So this is a sum over cubes of the lattice labeled by C. And then there's a sum over vertices labeled by V. And here we have a second sum over spatial directions, mu equals x, y, z. And there's an operator that lives on the vertex V, and it also has a mu index attached to it. So there are 3 kinds of these operators. All right. So now I have to explain what these are. Draw a picture of them. Okay, so BC is a product of X on the edges of a cube, right? Exactly what it sounds like. Involves right? It's a product over all the 12 edges of a cube. Okay, that's what BC is. So there's one of those terms for every cube. What's A, V, Z? Okay, so that lives on a vertex. So we can draw the 6 links coming out of a vertex. So this is the Z direction, X, Y, and we take a product of Z on these 4. So this is product of 4 Z's, but we don't include these 2 vertical links in the product, right? So Z is picked out here. This is an operator that lives in the XY plane, in the plane normal to Z. Okay. All right, I guess I can decorate this picture with some X's, but I'm not going to draw them all. And AX, V, AY, V are similar. You just take this picture and rotate it in the obvious way. So you get 3 terms. And then there are a couple properties to note. The most important one is that if you take any 2 of these terms, you can check that they commute with each other. Okay, so that tells us that this Hamiltonian is exactly solvable because we can diagonalize all of the terms. It's also true that if we square any of these terms, because it's just a product of Pauli's, we get the identity. And so that means that the energy eigenstates they're labeled by eigenvalues where BC can be plus or minus 1, AV mu can be plus or minus 1. So these are eigenvalues of these operators. Okay, so that's how the exact solvability works. It's just like the Z2 toric code. There's another sort of technical thing to note, which plays an important role. There's actually one local constraint among these operators. Yes, go ahead.
Are these Pauli matrices X?
Yeah, I did tell you what they are. So they're products of X's and Z's.
How do you have
That's what these pictures are. So the qubits live on links. They live on edges of the simple cubic lattice. Yeah. And so it's, yeah. So the pictures are supposed to define these terms in the Hamiltonian, right? So this BC is a product. You pick a cube in the lattice, and then you take a product of Pauli X over the 12 edges in the perimeter of that cube. And then for this one, you take a vertex AVZ, so you take a product over Pauli Z on these 4 edges, but not these 2 vertical ones. Yeah, so there's also a local constraint, which is something that's easy to check. If you take all of the A operators on a particular site, if you just multiply, if you multiply the 3 different A operators on any particular vertex, you get the identity. Okay, so one thing that tells you is that there's, you can't choose eigenvalues of these 3 operators independently because this constraint always has to be satisfied. It turns out that this is the only local constraint. There's no other local constraint. So every pattern of plus or minus 1 eigenvalues that satisfies this equation corresponds to a state it corresponds to an energy eigenstate of the system. Okay. No, this is just some operator identity. Okay, so right. So let me start by telling you, it's not the thing I want to focus on, so I won't really explain it. But I'll just make some assertions about ground state properties. So in infinite Euclidean space, if you study this model in infinite Euclidean space, there's a unique ground state, so no ground state degeneracy, just like the 2D toric code, okay? But maybe more interesting, if you consider an L by L by L cubic lattice with periodic boundary conditions, so an L by L by L 3 torus, then the ground state is degenerate, and the log base 2 of the ground state degeneracy is 6L minus 3. And all of these ground states are locally indistinguishable. But a property which is also true of the 4 ground states on a torus for the Z2 spin liquid. So this is one thing which is meant by topological order. So in this sense, these ground states have topological order in the sense that they're locally indistinguishable. You can make whatever measurements of local operators you want, but you will never be able to tell the difference between any of these ground states, even though there's a very large number of them. Yeah.
This may be a tangent. Are there any systems, quantum systems with no global symmetries, which in an infinite Euclidean space do not have a unique ground?
With fine tuning, yes. So at a first order phase transition. Yeah, anytime you have a first order phase transition, you'll have that. Yeah, I don't know if there are other examples. The other examples that I would think of are spontaneously broken symmetry. Okay.
from your temperature that.
Oh, it's sub-extensive because that's the linear system size. Yeah, it's not, so it's not L cubed. Yeah, so this is a sub-extensive ground state degeneracy. And I guess one interesting thing to notice about this is the -3 is what makes this particularly interesting. Because if it was just 6L, you could say, well, that's the same ground state degeneracy you'll get if you just stack up a bunch of 2D toric codes. And so if that were what you got, then you would worry that like maybe this model is just secretly a bunch of 2D toric codes. So we know that that's not true now from a variety of points of view, but that even with the -3, some people did worry about that in the early days of the model. But now we can prove that that's very definitely not the case. But the -3 is strongly suggestive that this is not just sort of coming from a 2D state that was sort of trivially put into 3 dimensions somehow. Okay, so, but what about excitations? That's kind of mainly what we're focusing on in these lectures. So there are 2 kinds. So BC equals -1 excitations, right? So the ground state has AV and BC equals to 1. Maybe I should say that. So the ground state right? So if we make any of these eigenvalues -1, that's an excitation. So cubes where BC is -1, it turns out that these are fractons. We'll call them F. And they behave kind of similarly to the fractons in the scalar charge theory, but they're Ising-like, so there are some differences, of course. And one thing that you note is that if you act with Pauli Z on a link coming out of the board, this is like a cross-section of a link, that link lives in the perimeter of 4 cubes. It touches 4 cubes, and you make 4 Fs on those surrounding cubes. So that's the way that you can create these excitations. You can create them in 4s. And so the mobility of these excitations is pretty similar to the charges in the scalar charge theory, but it's a sort of an Ising-like version of the same mobility. There's not really a conserved dipole moment here because these excitations are Ising-like, so you can't really think of it that way. Okay. But one thing you can do is you can take a composite of 2 of these Fs right on top of one another. They live on cubes. So let's say that this picks out an axis. We'll say it's the Z direction. This kind of excitation is called a fracton dipole in the literature. It's not great terminology because this is not really a dipole moment of any conserved charge. However, it is a pretty geometrically evocative term, so it's kind of nice that way. So you can ask about the mobility of this excitation. Well, you can actually see from this picture, because you can put Fs in this sort of configuration, and they're Ising-like, you can destroy 2 Fs here and recreate them over there. So that will actually take this fracton dipole and move it over, say in the X direction, and you can do the same thing in the Y direction. So this is an excitation that we call a planon, another kind of restricted mobility excitation, and it moves in the plane perpendicular to the quote-unquote dipole moment, perpendicular to Z. Okay, so again, this is sort of a similar theme to what happens in the scalar charge theory. Okay. All right. So and of course, you can make these fracton dipoles in any direction. So there are planons moving in X, Y, Y, Z, and X, Z planes. The model has a cubic symmetry. Yeah. Well, right. So I said there's not really a dipole moment, right? So that's not precise. But all I mean, you can take a stack of two neighboring cubes in the z direction, the x direction, or the y direction. That's all it means.
There's still an axis.
There's an axis, right? Yeah, I don't care about which way it points. Yeah. Yeah, yeah. So that's one of the things that's not precise about, you know, using the term dipole here. Yeah, there are like the other thing that's not precise is that if you can ask like, what if this F was 2 cubes above the first one? And for a reasonable definition of dipole moment, because it's an Ising-like charge, you would actually get 0. In certain ways of defining it. But that excitation is also a non-trivial planon that moves in the xz plane. So, you know, this, maybe I should put lots of quotes around dipole here. There's not really a dipole of anything, but it's just the term that people use. Yeah. So planon is a general term. It's like fracton. So a planon is a restricted mobility excitation that can move within a plane, but it can't move perpendicular to the plane. So its mobility is less restricted than a fracton, which can't move at all. And a fracton dipole is just a name for this particular excitation in the x cube model. But planon is a general term. It describes excitations in a lot of systems. In this case, the planon is a bound state of 2 fractons. Right. So the way that you would create a planon out of nothing, you can make 4 fractons, and then those 2 pairs are fracton dipoles, and they can be separated. Yeah. So So there are string operators that create fracton dipoles at both ends. But those string operators are confined to live in particular planes. You can't take a string operator and bend it out of the plane in which it's mobile. Yeah. So this is a link that's coming out of the board, right? I can draw, right. So these are, so these are cube centers of the simple cubic lattice, okay? And this is a link, right? If you have 4 cubes, this is really hard to draw. That's why I didn't try to draw a 3-dimensional picture. But if you have 4 cubes in the cubic lattice, right, they meet and they share, you can have 4 neighboring cubes that share a common edge. That's where you act with this Z. It lives on the common edge shared by 4 cubes. It lives at the center of a cube. Yeah. Pauli Z lives on an edge. Yeah. It lives on a vertical edge, right? And these Fs live on cubes that touch that vertical edge. Yeah. Right. Yeah. You can derive this picture from, right. I mean, it's an exercise to derive that picture from the definition of the Hamiltonian.
That operator is not in the Hamiltonian, it's a local operator, the Z operator.
Yeah, the Z operator is not in the, if you add it to the Hamiltonian, you'll break the exact solvability, but it will give you some dynamics. Yeah.
If it's weak, then it's still confined.
Yeah, that's right. Yeah. So this is a gap phase. It's stable. Yeah. Yeah. Right. There's no term you can add to the Hamiltonian that will give fractons hopping dynamics, that will destroy a fracton somewhere and create it somewhere else. So that you can prove that statement. I haven't proved that statement, but it is something that you can prove rigorously. So there's just simply no local operator that does that. So in fact, the sort of dynamics that you can add is of the character of what you get if you just add Z to the Hamiltonian. You'll have terms that create and destroy fractons in these groups of 4, and that gives you some dynamics, but it's not hopping dynamics. It's some more interesting cooperative dynamics. Yeah. What I didn't quite catch that. Can you just say it again? Yeah. Oh. So you're saying like if you try to modify the AV terms so that they look like the vertex term in the 3D toric code. Well, the problem with doing that is that you break the exact solvability. So if you do that but don't do anything else, then that term will not commute with BC anymore. So you get, yeah. So yeah, I mean you can change that. Yeah, so it's not clear what that model will do. I think it's true that if you say like make that change to the AV operators, then you can ask like find some X operators that commute with them. You're just going to arrive at the 3D toric code if you do that. That will kind of take you back to the 3D toric code. Yeah.
Being in the center of each cube.
Yes. Yeah.
Is there any way to actually create these four fractals? There's no way to separate them into like being individual fractals.
You can separate them into being individual fractons. You need to act with Z's kind of on a whole membrane. So I can draw a picture of that, right? So if you take a slice through your cubic lattice that's pierced by a bunch of perpendicular edges, that's what these dots represent, then what you do is you'll create F's at the corners of this operator. So these are all Z's. Yeah. So there in this, you can do this on any rectangular membrane, living in a lattice plane. Yeah.
That's like cooperative mobility.
That's the kind of that's how the cooperative mobility works in this particular model. Yeah. Okay. So let's see. Right. All right, let me think about what I want to say next. Yeah, so in this example, so there are some other interesting excitations. In this model. If you just call the fractons electric excitations, these other excitations are like the magnetic excitations. And these are just the AV excitations, okay? So the kind of excitation that you can make is an excitation like AVX equals AVY equals -1, but still AVZ equals 1 on some vertex. We can't just make one of these -1 because of this local constraint, right? So we can't make just say AVX equal to -1. That's not possible. So this is an excitation that lives on a vertex. And the way that we would create this excitation, so this is an excitation that lives on, the way that we can make these excitations is that we can act with X, in this case, on a vertical link. So this is the Z direction, X, Y. This is a vertical link of the lattice. This will create, so let's call this excitation L sub Z, will create 2 of these L sub Z excitations on 2 neighboring vertices. Okay, now clearly these excitations are at least somewhat mobile because we created them in this vertical pair, and we can keep doing this process so we can arbitrarily separate these 2 in the Z direction as far as we want. Another way to put it is by taking a product of X on a stack of vertical links, we have a string operator for this LZ excitation. Okay, so it's mobile along this line. It turns out, though, that it's not mobile otherwise, so it can't move off the line. Okay, so I'll explain what happens if you try to move it off the line. But let me just first say, so this is only mobile in the Z direction, and it's called excitations with this kind of mobility are called line-ons. So this sort of excitation is called a line-on. Okay. So what happens if you try to take one of these line-ons and move it in the X or Y direction? Right, so imagine that we have an LZ excitation here. So again, let me draw some axes. This is Z, X, Y. So I'm drawing a picture in the XZ plane. So I would like to move this excitation first here, which I can do. And then I'd like to move it over here. Okay, so I want to display this excitation. And I want to create a new LZ excitation over here. Well, it turns out that I can't do that unless I also create some other excitation here. It turns out that the excitation you leave behind is an LY excitation, right? And drawing these arrows as curved was probably a bad idea. Shouldn't do that. Oh yeah, and in fact, sorry, what you can put here is not an LZ excitation. It's just some other, right? So clearly we can rotate this picture in different ways, and there are also X and Y versions of this excitation, just by the cubic symmetry of the model. If you want to take this LZ and move it over here, the best you can do is leave behind some other excitation at the corner, and then you can make an LX excitation that will move off in this direction, right? So this is some extra excitation, and so that means that, you know, this is another kind of cooperative mobility, right? You can move this line-on off the line, but at the expense of leaving something behind at the corner. Yeah. Sorry, what was the question again?
Z operator on the bar to generate to flip the sign of both AX and AY. Why change the X?
Well, because AX and AY are made out of Z's, right? So you're asking, like, why does this X operator like create that state? So that's just because AX and AY, they're products of Pauli Z. And yeah, the A operators are made out of Pauli Z, so that anti-commutes with X. Yeah, right. And it anti-commutes with AX and AY because those have a Z in the vertical direction. They have Z's in the vertical direction, but AZ has no Z operators in the vertical direction. So this operator commutes with all the AVZs. Yeah. Okay. So right. Okay. And another point to make is that you can also make planons, just like we made planons out of fractons, you can make planons out of line-ons. So with the same axes, if you take two LXs and put them on top of each other, well, clearly this can move to the right, but it turns out that it can also move in the Y direction into the board. And this is called a line-on dipole. It's a composite, it's a planon. And it's a composite of two line-ons. Okay. Good. So, right. Okay. So now there's another statement I want to make about these excitations. You might imagine. So there's a sort of trivial way to get restricted mobility excitations like these. Just a second. The most trivial way of doing it is something I already alluded to. You can just take a stack of 2D toric codes all in one direction and put that in 3 dimensions, and those excitations will be planons. And actually, that should really be thought of as the simplest example of what we would call a fracton state. So fracton states are just those that have some restricted mobility excitations. And so that really should be thought of as kind of a trivial example of a fracton state. Okay. All right, that's not very interesting. You can do something slightly more interesting where you stack toric codes, 2D toric codes along all 3 principal axes of the cubic lattice. Okay, so then you'll have planons moving in 3 different orientations of planes. And in that sort of a system, you can actually make fractons and linons. The way you would make a fracton is you would do something like take a E excitation in 3 different toric code layers of 3 different orientations and bind those together. And that will be an excitation that's immobile. Okay, so it is a legitimate fracton, but there's something kind of not so interesting about it. And so what is possible to prove, you can prove this rigorously. I don't have time to explain in the proof, but I can tell you after. So it's possible to prove that F is not in the X cube model. It's not a composite of any linons and planons. So the fractons in the X cube model are not composites of excitations that have higher mobility. And similarly, LZ is not a composite of any planons. So we would say the term for this is that both the fractons and linons in this model they're called intrinsic. Just means that they're not composites of higher mobility excitation. So that tells us that something intrinsically 3-dimensional is happening, right? This is not just coming from, right? In this stack of toric codes type examples, what's uninteresting about the fractons you can make in that example is they're not intrinsic. They're a composite of a bunch of planons. Okay, but it's possible to show that this is not the case in the X cube model. Yeah.
The statutory codes, this is not allowing copy.
Well, I mean, there's no way to hop from layer to layer. It's not you don't need any symmetry. You don't need to fine tune. If you stack a bunch of 2D toric codes, there's no way for an E to get from one layer to the next layer up. Yeah. Mm-hmm. Yeah, that's right. Okay, so right. So another point I want to make, so this connects back to something else from yesterday, is that the X cube model is not described by any, at least conventional, topological quantum field theory. Remember, I gave this discussion of what it means for a field theory to be a TQFT yesterday. And the X cube model cannot be described by any TQFT. Why? The simplest thing to say is that the ground state degeneracy, it depends on the system size, right? Whereas for a TQFT, the ground state degeneracy, first of all, should be finite. And second of all, it should only depend on the topology of the spatial manifold. And maybe even a better reason is that you can't just, even to define the X cube model, you can't even define the X cube model on a general spatial manifold. We don't know of any way to do that. And you can argue you need something called a foliation structure to define something like the X cube model on a general manifold. What's a foliation structure? Well, roughly, it's just a slicing of space into layers. You actually need 3 different kinds of layers for the X cube model. But this is a kind of geometrical structure that, you could imagine a TQFT that likes to take manifolds with this foliation structure as input, but it will not be a conventional TQFT in any sense because it will spit out either, well, I don't know what it will spit out, but it won't spit out finite dimensional vector spaces. And so, this, this is an example of a gap phase that doesn't have a TQFT description. And I said conventional because maybe someone will figure out how to generalize TQFT so that something like TQFT can be applied here. But it's not like there are unconventional TQFTs that are known that can describe the X cube model. Yeah.
So I don't know a lot about TQFTs, but if I just want to think in Indian space, but isn't the weak thing really interesting in terms of the density thing? Like in the usual case, TQFT tells you also something about the statistics of the anions or something like that, right?
Yeah, that's true.
What would you want? I mean, why would you need a TQFT in this case if you don't have any kind of braiding or anything?
There is braiding. There is braiding. I'm going to tell you about that. So, yeah, I mean, we don't necessarily need it, right? We can come up with other ways of describing all the phenomena. But the main reason, I'll tell you why I'm mentioning this in a second, actually, but there's another question back there that I want to answer first. Yeah. No, they're not. No, they're not bound. I mean, you could add a term to the Hamiltonian that's like a short range attractive interaction between them or something. So you can consider composites of Fs and Ls. Those are kind of interesting objects, but. I mean, you can make various composites of all of these excitations, right? So, I mean, like one important point to make is that there are actually lots of excitations that you can make in this model. They're all built out of these Fs and Ls, but they're also all distinct excitations. And there's actually, there's actually an infinite number of different excitation types, very different from what happens in 2 dimensions. I'll answer your question in a minute because I wanted to say something that goes back to the previous question. So this is kind of an important point. So we know we didn't used to think that this was true. Actually, we know that gap phase from this and other similar examples, that gap phases are not the same as topological phases. What do I mean by a topological phase? I think the definition of topological phase that I like is that a TQFT description exists. Some low energy TQFT description exists. So it used to be conventional wisdom that actually every gap phase had a low energy TQFT description. There are probably a lot of reasons even from a long time ago that we shouldn't have thought that was true. But nonetheless, this was definitely conventional wisdom that many people believed. I think basically well, I'm not sure there's anyone who really questioned it actually. But now we know that this is not true. So gap phases and topological phases are not the same thing. This is one of the reasons why fracton theory is challenging actually. Okay, so one of the reasons that we made such rapid progress understanding topological phases is because we, one, already understood a lot about TQFT, and 2, TQFT is simple enough that the things that we didn't already understand, kind of soon after topological insulators were discovered, we were able to understand pretty quickly. Because TQFT is sort of a world where a lot of things are very tractable. You can answer lots of questions. There are many different approaches to TQFT and structures that come out of it. There's a lot that you can do, okay? But we don't have that framework for fracton phases. That's one reason why it's hard, and that's one reason that's a lot harder than say gap topological spin liquids like the Z2 spin liquid. Did you still have a question? No, no, there's no photon. So this is a fully gapped state. All the excitations are gapped.
Is there a model that has a photon?
Well, I don't know what you mean. I mean, this model, this phase doesn't have a photon excitation. The scalar charge example that I told you about does have a photon excitation. So I mean, that's whether or not a given fracton phase has a photon-like excitation is a universal property of that phase. Yeah.
Yes, if somebody wrote down a model, a lattice model of spin that has a gapless photon and some fracton.
Well, yeah, so those are the models we know like that are these tensor gauge theories. Yeah. But that will never happen in a commuting Pauli Hamiltonian because you know, the excitations are always gapped, unless you forgot to add some terms to your Hamiltonian that you should have added, in which case you get lots of gapless excitations. But that's not a photon, that's just fine tuning. Yeah, in commuting Pauli Hamiltonians, you can't get something like a gapless photon. Okay. So, yeah, all right. So we don't have much time left. So I think, but maybe we have a few minutes. So I'm going to make some comments on the sort of second to last thing I wanted to talk about, and I won't talk about the last thing. Right. So there was a question basically whether there's some kind of braiding here. So it turns out actually that there is a lot of interesting statistics in the X-cube model and in other models that are like the X-cube model, other gap models with fractons and other restricted mobility excitations. The first thing to say is just that, you know, just to remind ourselves about some more familiar things. So if you have what if you have completely mobile particles in 3 dimensions? So just mobile point-like excitations. So if you have an excitation A and B, you could ask, like, is there some kind of mutual statistics between A and B? Well, there's not, because if you brought A in a loop around B, you can deform this process so that eventually you can take the loop along which you move A and you can shrink it down to nothing, right? You just lift it off the plane where B sits and then you shrink it down. So in 3 dimensions, you can certainly do this. So there's no mutual statistics of point particles in 3 dimensions. You can ask about self-statistics. So this is a little bit more interesting. But it turns out that that 2 exchanges is the same as 1 full braid, where 1A is brought all the way around the other one, which is trivial by the argument above. So I'm not giving you an argument for this. It's a little harder to visualize, but this is true. And so this implies that the only possibilities for self-statistics are bosons and fermions in 3 dimensions for fully mobile particles. So this is a very well-known fact for a very long time. You know, these arguments, of course, assume from the very beginning that the excitations are mobile, and things change very dramatically once you start to have restricted mobility excitations. Okay, the simplest thing that you can do you can have plane-on statistics. Okay, so let's draw a z-axis. Let's imagine that we have a plane on here, which moves in this xy plane, and we have some other plane on here, which moves in some other xy plane, and let's say they're separated by some distance, delta z. Well, we can definitely take A, and we can move it in a loop that encircles B. Let's draw a line below B to keep track of where B is in projection. So we can move A around this loop. And as long as A and B are not too far apart, we can, in the vertical direction, we can get something non-trivial. If A and B are very far apart, then we don't expect to get anything. But there can be some kind of mutual statistics. And it can be non-zero. It can be non-zero if delta z is not too large. And how large is going to depend on details of the particular system that we're considering. Okay, and so for example, in the X-cube model, we have 2 kinds of planons. There are these fracton dipoles and line-on dipoles, and they have they have non-trivial such mutual statistics. So this, I won't, so this, as long as they're close. So this happens for fracton. This happens for the fracton and line-on dipoles in the X cube model. It's not hard to derive this. Actually, all you need to do is find the string operators that transport these two kinds of excitations. And all you need to do is show that those two string operators anti-commute, which is not that surprising because the strings for, I'm going to mix up which is which. The strings for the fracton dipoles are made out of Z's and the strings for the line-on dipoles are made out of X. So not that surprising that they can anti-commute with one another. Okay, so it's really just analogous to what happens in the 2D toric code. So that's kind of, this is sort of moderately interesting, but it's very 2D-like. And so maybe not that surprising. So I'll show there, but there are more interesting things that can happen for which it's harder to draw pictures on the blackboard. So I have some better pictures that I will show you on the screen. Okay, so there are three different examples that I can quickly flash a picture of. So there's mutual statistics between fractons. This is all, so all of this you can think of for the X cube model, but there are also generalizations of this to other models. So the fractons and line-ons have mutual statistics. And the way it works is you can consider a process where you start with one fracton and one line-on, and then you can use the cooperative mobility of the fracton to split it into three, going from 1 to 2. Then you can move the line-on through the plane in which you move the fractons. And then you can bring the fractons back to the origin using the inverse of the same operation. And then you can bring the line-on back. And what happens here, if you think about this process in terms of operators that you act with, there's a membrane operator for the fractons, and there's a string operator for the line-ons. And those two operators anti-commute where the string operator pierces the membrane operator. And that's the source of this mutual statistics, which is pi in the X cube model. Okay, so that's, relatively simple. You can also ask about self-statistics. So this is a little bit more interesting, actually. So you might naively think that if you have two line-ons moving on the same line, there's no way to talk about their self-statistics, because in order to take two particles and exchange them, you have to be able to exchange their positions without them ever getting close together, right? Whenever you talk about statistics, you always want to keep excitations very far apart, because once they get close together, there will be some kind of boring interaction between them, just coming from whatever details you have in the Hamiltonian. There could be some attractive or repulsive potential or whatever. And that interaction will generate all kinds of local phase factors in the time evolution, which will scramble any statistical phase. So normally, that's why we would say there's no braiding statistics in one dimension, right? Because we can't have particles exchange in one dimension while staying far apart from one another. However, line-ons in the X cube model can exchange. And the way that you do it is to use cooperative mobility to your advantage. So here, this is so 1 is an initial state with two line-ons. And in the first step, the line-on in the top left, you have to move it off the line that it lives on. And you can do that at the expense by creating 3 other line-ons that live on different lines. Then you can take the first line-on, or sorry, the second line-on and move it to the position of the first one, which now got out of its way. And then you can bring these the 3 other line-ons that you created, you can move them over, use the cooperative mobility, and put them back into this position, and then you wind up exchanging the 2 excitations. So if you do this in the X cube model, you actually get nothing. This statistical phase is 0, but it can be non-trivial, and there's a variant of the X cube model where it's non-trivial, and there's an interesting story there, which I'm not going to have time to tell you. Okay, and maybe the most exotic thing, which is something that we really only understood pretty recently, is that even fractons, the most extreme example, even immobile fractons can have self-statistics. And the idea is very similar to what I showed you for line-on self-statistics, that you need to be, the two fractons have to be able to get out of each other's way using the cooperative mobility. And so the way that it works is something like, so the black excitation is a fracton sitting at the origin, and the orange excitations you can think of as being the same as an orange fracton that used to sit at the origin, but it was moved off by cooperative mobility, right? So in principle, you might be able to find a way to exchange the black excitation with the composite of all of the orange excitations. And if you can do that, you can get a non-trivial statistical phase. And so this is a sequence of moves that does that. Basically, you just kind of keep moving these excitations out of each other's way. So you bring one away from the origin, you bring the other one back, you have to take it away from the origin again, and you kind of repeat that process. And eventually, while always keeping the excitations far apart, you can switch the orange and black labels. And again, if you do this in the X cube model, you don't get anything interesting, but you can get a non-trivial statistical phase in other models, even in variants of more complicated fracton models like Haas code. And again, there are some interesting stories to tell about that, which I'm not going to have time to tell you. I also didn't have time to tell you a little bit about what's currently happening in fracton physics, at least the more formal side of it, which is what I'm mostly thinking about at the moment. But if people want to come up after the lecture, I'm happy to tell a little bit about that. But I think we're at our time, so we should probably stop.
A couple of questions and then we'll break the.
Yeah. Yeah, okay, that's a good question. I would say that's right. So I didn't really give a definition of what I mean by a fracton phase in these talks, but the definition that I usually use would be that, let's consider models without any special symmetries except perhaps translation symmetry. And then if we find restricted mobility excitations, those are, fractons, so such phases with restricted mobility excitations are fracton phases. So under that definition, that's not a fracton phase, but it's clearly fracton-like, right? And there's a whole, so it's definitely part of the subject of fracton physics, and there are very close connections between states like that and fracton phases that actually meet my more restrictive definition. So for instance, one kind of formal connection is that if you have a system like that, then there's some dipolar symmetry. If you gauge that dipolar symmetry, then you'll get to something like the scalar charge theory. So there are connections like that, but also systems with dipolar symmetries are interesting in their own right? If you just consider the dynamics of those systems, there's a lot of interesting stuff that you can find both in equilibrium and out of equilibrium. So it's, it's not a fracton phase under the definition that I usually I would say it's like a, fracton-like phenomenon or something like that, but it's all kind of part of the same subject. Yeah. Go ahead. Okay, so, right. Essentially, there can be, and there are, one interesting thing that can happen is you can have, what you can do is you can condense pairs of E excitations or M excitations. But let's say you condense pairs of E excitations in neighboring layers. So, and then you can ask what's the phase on the other side of that condensation transition. So that's actually the same phase as the 3D toric code. So after you condense those pairs of E's, then the E excitation becomes fully mobile. And it turns out that the M excitations get confined into a string-like excitation, which you can still make under that sort of condensation. So, I mean, I think other things can happen probably, but that's the simplest thing that you can imagine. A lot of questions. Okay, let's start from there.
There's some generalization of like LSM constraint that given the some ground state degeneracy, if I have a model, I will get fraction order, or
That's a good question. Yeah. So,
I don't break it through.
so I think that it may be true, and I think maybe this was actually even worked out. So I think that, so for ordinary symmetries combined with lattice symmetries, I don't think that LSM constraints ever work that way. Like, I don't think that there's ever an LSM constraint that requires fracton order to satisfy it in a symmetry preserving gapped state. If you consider subsystem symmetries, which are symmetries that act on certain subspaces of your space, like planes or something like that, then I think that's likely possible. And I could point you to a reference where I think that was perhaps worked out. I think that's, yeah, I don't want to say what it is online because I'm not 100% sure that's what's really contained in that paper, but I think at least some of that has been thought about in the literature. Yeah.
You have the paradigm.
Yeah.
Based on subsystem.
Yeah. So the answer is yes. Yeah. So this is an important perspective that I just didn't have time to talk about. So, right. In general, it's true that if you take a system with subsystem symmetries like I just described and you gauge it, you get some fracton system. And in fact, that was actually a point of view that comes from the VJ Ha and Fu paper, as well as another paper at about the same time by Dominic Williamson. So that started a whole subject of thinking about subsystem symmetries and, what can you have, if you suppose you have a system just with a subsystem symmetry, what interesting kind of states can you have? And there's a connection with fracton phases. So there's a very big story to tell about the role of subsystem symmetry in all of this, which I didn't talk about just for lack of time. Yeah. Yes.
Do you have any thoughts like realistic that might realize this sort of phase?
I have some thoughts. I don't know if they're like very good thoughts, but so one route to try to realize fracton phases, it's sort of, you could imagine, this is based on something I didn't actually have time to talk about for the U1 spin liquid yesterday. I kind of alluded to it, but basically, so the way that you can realize any gauge theory, one way to realize a gauge theory in a spin system is to start with a degree of freedom which you can think of as like a lattice vector field. Or, I mean, for a fracton system, it would be something like a tensor field. But you start with a lattice vector field, let's say, and then you energetically impose the Gauss's law constraint. You'd have a term in your Hamiltonian like divergence of E squared. And if you make that term large, then basically what you can show is the resulting system. First of all, you can exactly write it as a gauge theory. The key, that's a little bit of a trivial statement almost. The interesting question is whether that gauge theory could go into a deconfined phase. Adding this divergence of E squared like term will at least make the electrically charged matter gapped. And then you have to worry about what happens in the magnetic sector of the gauge theory. And that's sort of the story behind quantum spin ice in pyrochlores. That's sort of how you could realize a U1 spin liquid on the pyrochlore lattice. If you can find a tensor gauge theory where the Gauss's law constraint could actually be implemented energetically with reasonable interactions on a reasonable lattice, that would be a promising way to find fractons. So I've always wanted to find something like that, but it's not so easy because most of the tensor gauge theories that you can write down, they tend to, the electric field involves lots of components, and it's sort of hard to think about like how you should put that down on a lattice in such a way that the Gauss's law constraint becomes something natural from an energetics point of view. And then it needs to be a lattice which is actually realized in, some real class of solids. I'm thinking mainly about solid state realizations. I mean, you can always imagine trying to build these models in various kinds of synthetic quantum matter. That's maybe more challenging than other proposals though, because it's all of this physics is in 3 dimensions. So that does make it harder for some of those kinds of setups. But anyway, those are the thoughts that I have. Yeah, I'm sure that there, maybe I'll make a more general comment actually, which is that, it's, right. So the subject of fractons is sort of heavily based on these exactly solvable models with very complicated multi-body interactions, which are not realistic at all. And so because of that, I think that some people have a reaction like, oh, this has nothing to do with reality. But I think that's a very misguided reaction because the subject of quantum spin liquids like Z2 and U1 quantum spin liquids, it could have been developed in that way too. And that's just not how it developed. But we also have those complicated, exactly solvable models there. What's harder to do in fracton phases is to do sort of a useful parton theory, where you start with a realistic spin model, and then you try to do some kind of a mean field theory where you split your spin into a bunch of fractons or something like that. You can do that. The problem is that the mean field Hamiltonian that you get actually involves multi-body interactions of the partons themselves. So the mean field Hamiltonian is actually strongly interacting. So it's not so useful. But this is really a technical thing. There's nothing, right? This is more about what we can do as theorists. It's not about what actually happens in real spin models. But because of that technical thing, because there's nothing like parton mean field theory or Gutzwiller projective wave functions or those tools, which played an important role in the development of thinking about spin liquids in real materials, you could be misled and think this doesn't have anything to do with actual realistic spin systems. But I don't think that's true. I just think that part of the theory is quite challenging to develop. And so maybe there's an opportunity there, but I think it's also pretty hard. But that also means that there's no reason that these states can't occur in any number of real frustrated spin models in 3 dimensions. We just don't really have the technical tools to think about, in what sorts of spin models they might occur. I would also say, in terms of actually predicting when spin liquids occur in real spin models, more conventional spin liquids, those technical tools have a terrible track record. This is awful, actually, really, really bad. So it's all, that's sort of another point to make, which is that yeah, those tools exist, but they sort of failed actually in the conventional spin liquid case. So, so it's sort of, you shouldn't really make too much of that. Maybe we'll discover, maybe the first experiment that conclusively discovers a spin liquid will discover a fracton spin liquid rather than a more conventional one. I don't know. Probably not, but maybe.
Thank Mike again.